Hello. In our previous work, we saw how as we took secants and we brought one endpoint of the secant closer and closer to the other, that we approached the slope of the tangent line. So these were called the limiting values of those slopes. Now let's turn to functions. So if I have this function f of x here, and I used x squared minus x plus 2, the tables below show the values of f of x as x values get closer and closer to the number 2. So looking at some values here, we start with putting in 1 for x, and our output is 2. But as we go down the list, you can see that our f of x gets closer and closer to the number 4. Same as if we go from the other side. If we start from 3, we get a value of 8, but as we get closer and closer to 2, we get closer and closer f of x values to 4. So what we can say is that the limit as x approaches 2 of x squared minus x plus 2 is 4. So to kind of restate what we were saying before, as the x values we choose get nearer and nearer to the value of 2, the y values get nearer and nearer to the value of 4. And if I were to draw the graph of x squared minus x plus 2, I'll have the point 2 comma 4 here, and as we get closer and closer to that value from either side, my y values will get closer and closer to 4. So let's use this to talk about the definition of limits. So the definition of a limit. We read this first phrase here as limit of f of x as x approaches a equals L. So we can get our values of f of x very, very, very close to the value of L as we start picking x's very, very close to the value of a. Now as we do the approach of these values, notice that we're not picking values for x that are the same as a, but just getting closer and closer to that value of a. Another way to state this down here, as f of x approaches the value of L, our values of x must be approaching the value of a. So let's take a look at these. In these three different graphs, I'm looking at the limit of f of x as x approaches 1. So notice that in this first graph, here's my value of where x is 1 right there. And that's at the ordered pair 1, 2. So as I get closer and closer to that value of 1 for x, so as x gets closer to 1, f of x is getting closer and closer to, I should put an arrow there, f of x is getting closer and closer to 2. You can see how here I have the ordered pair 0, 1. This would be 0.5, 1.5. This is 0.9, 1.9, and so on. So as I get closer to 1 for x, I get closer to 2 for f of x. Let's look at the one below it. I'm still approaching 1, but notice we have some little difference going on here in this. My 1 value is undefined. Right? So we're at 1 comma some undefined number. I have a hole in the graph there where I don't have an f of x value when x is 1. But it's not about what we are equal to at 1. It's about what number we get closer to as we get closer to 1. So as x approaches 1, f of x is still approaching the number 2. We still have those same numbers, 0, 1, 0.5, 1.5, 0.9, 1.9, and so on. So as x gets closer to 1, here we go, we'll put that in, f of x has to get closer to 2. In the third one, I still have that open circle right there, so I still have the ordered pair. Well, it's not really an ordered pair, I guess. We're just undefined at the value of 1. Except we have a function still, because when I put in 1, instead now I'm getting 1 instead of 2. But if we look at f of x, as we get closer to that value from either side, as I put in 0, 1, 0.5, 1.5, 0.9, 1.9, as x gets closer to 1, my f of x values are still approaching the number 2. Again, it's not about what x equals at 1, it's about the approach as we get there. Okay, so that's our basic definition of limits. We'll do more examples of this when we get into class together. So for now, we are done.